Hi everyone. Today we're going to finish up our notes on L'Hopital's rule. So let's get going. So last time we did a little bit of limit review and then we talked about what is required to use L'Hopital's rule, and then we did examples 1 and 2 where we talked about indeterminate forms and what your work should look like when doing L'Hopital's rule on a free response question. So let's keep going. Let's take a look at example 3. Before we start that example, let's come to the side here and review a little bit of algebra 2. So if I have e to the natural log of anything, right, well, that is going to be the equivalent to whatever the anything is. Okay, and that's because e to the natural log of something is a composition of inverse functions, right? So those technically cancel each other out. And now we can basically apply this in reverse when we're talking about taking the limit of something. So if I'm taking the limit of anything, right, I can go ahead and think of it as the limit of e to the natural log of that thing. Okay, and this is something that will come into play for us in a little bit. So let's take a look at our example. And so the first thing to notice here, limit as x approaches infinity, and I've highlighted this in the orange here, right, which is we have a something with a variable raised to a variable power, okay? And now when we have something like this, right, what we can do is we can say, I'm actually not going to do the limit of this function. Instead, what I'm going to do is the limit of the natural log of that function. And so again, here's my function, 1 plus 1 over x to the x, and now technically I should have some brackets or something around all of this, right? Because all of that is inside of my natural log. So again, I am not doing the limit I've been asked to evaluate. I'm doing the limit of the natural log of what I've been asked to evaluate. So again, I only do this when I have variable, right? I have the x down there, to a variable power. And so why would I do this? Well, log properties, right? I can take this x and I can bring it out in front. And so I can rewrite this as limit as x approaches infinity of x times that whole natural log. And now remember, the indeterminate forms we are dealing with are 0 over 0 or infinity over infinity. So in other words, I need a fraction, okay? And so I'm going to take this x, and now instead of doing what we did on example 2, where we said, okay, I'm going to just replace x with something else, and I redid the question in terms of a different variable, instead of doing that, right, I am going to instead just take this x in front and I am going to just rewrite it as the quotient of its reciprocal. So instead of x times that, I'm going to say dividing by 1 over x. And now L'Hopital's rule is applicable, right? If I plug in a very large number here, this goes to 0. Natural log of 1 is 0. 1 over infinity, that also goes to 0. Remember, we never want to write in our work that this is 0 over 0, right? We don't want to write that in our work. We want to set it up like we did on example 1 yesterday, right? We want to show limit of the numerator and denominator separately. We want to make sure we say that both numerator and denominator are differentiable, okay? We never want to write indeterminate forms in our work. So no 0 over 0 in my work, no infinity over infinity in my work. Okay, but L'Hopital's rule will apply. So let's start with the derivative of the denominator, which is going to be negative 1 over x squared. And there's a little spoiler there that will cancel out. With what? Let's find out. So in my numerator, I have to apply chain rule. Derivative of the natural log of anything is the reciprocal function, right? So I can write 1 over 1 plus 1 over x. And now, chain rule, what's the derivative of 1 plus 1 over x? Well, it's just the derivative of that 1 over x. And so again, I get negative 1 over x squared. And so these two cancel out. And so I am left with just the limit of 1 over 1 plus x. And now if I am going to let x approach infinity, this goes to 0. 1 over 1 plus 0 is just 1 over 1, which is 1. Now, remember, I just solved a limit I was not asked to solve, right? I did not evaluate the limit I was asked to evaluate. I found a completely different limit. But here's what I can do now. I can take the limit I was asked to solve and I can rewrite it as e to the natural log of what my function was in the limit. So again, here's the limit I was asked to solve. Okay, I'm going to rewrite this as limit as x approaches infinity of e to the natural log of 1 plus 1 over x to the x. And now this part, the exponent of the e here, right, is what I just evaluated to be 1. And so this whole thing becomes e to the first power, right? And the limit of any constant is itself. And so this just becomes e to the first, which we know is e. Okay, so a little trickery here, right? And so again, the key thing here, how did I know to do this one this way? The thing we were looking for is variable to a variable, right? Instead of trying to tackle this one, I'm going to take the natural log, bring the exponent down using the log property, rewrite it as a quotient, and now I can use L'Hopital's rule. I get a limit that I'm not been asked to solve, right? But I can take the limit I was asked to solve, rewrite it as e to the natural log of that function, right? And then I can plug in the value I found. So a little bit of trickeration there, okay? Let's look at example 4, same thing, okay? Limit as x approaches 0, sine of x to the x power, okay? And so, again, this is sine of x to the x. So just to be clear here, I should put parentheses or something around the sign. Okay, so again, I have variable to a variable, right? So instead of trying to tackle this limit, I am going to do natural log of sine of x to the x power, which allows me to use my log property that brings the x down in front. And just like last time, I can rewrite that x as 1 over x in my denominator, and now I have a quotient. And so let's see if L'Hopital's rule would apply here. So if I plug 0 into this, sine of 0 is 0. Now remember, natural log, I'm not actually plugging in 0, I'm plugging in something that's approaching 0. And so if you remember what happens to natural log, let's do a quick graph here on the side, right? What does natural log look like? It looks like that, right? It looks like that. As x is approaching 0, right, natural log function is going down, down, down to negative infinity, okay? And so, right, with 1 over x, it's kind of the same idea as x is approaching 0. Now, technically, since I can only deal with this on the right-hand side with the natural log, it's the same thing, right? So it's a different infinity. It would be positive infinity, but infinity over infinity, it's still indeterminate, okay? So let's go ahead and do our derivatives. So 1 over sine of x, right? So again, derivative of natural log is the reciprocal. Chain rule, I get cosine. Derivative of 1 over x, I get negative 1 over x squared, right? And so can I plug 0 into this, right? Now, you got to be careful here, right? Negative 1 over x squared, I'm actually going to rewrite this so that the negative x squared is in the numerator and the sine of x is in the denominator, okay? So can I plug 0 into this? So this becomes 0 on top, so 0 times 1, right? And then the bottom is 0, so this is indeterminate again, right? And so I have to do L'Hopital's rule one more time, okay? And so for the numerator, I have to do the product rule, right? So negative x squared times derivative of cosine is negative sine, right? Plus the derivative of negative x squared is negative 2x. That's why there's no plus here, times cosine. And for the bottom, it's just the derivative of sine, which is cosine. Okay, can I plug 0 into this? Yes, we can. This whole thing is 0. This whole thing is 0. This is 1. And so we do all of this, and we get 0 over 1, which is 0. And so remember, this was not even the limit we were asked to find, right? I was asked to find limit sine of x to the x, which I'm going to rewrite as limit as x approaches 0, e to the natural log of sine of x to the x. But I already know that this whole thing is getting to 0. And so I get e to the 0, which is 1. Okay, so just a couple of examples here, right? I like example 4 a lot, this multiple L'Hopital's rule thing. This is something that can definitely show up on a free response or, multiple choice question on the AP test as well. Okay, all right, that's it for now. I will see you guys next time.